that brings me to the next chapter, a very important chapter. We will now move from cell to pack. Let us get into what is called battery pack development. So far we are talking about cells. Now, the pack behavior will be built on cell behavior. So, if I have my cell has a maximum voltage of 4.2 volts, and if I put 10 cells in series, I will get 42 volts. Pack behavior will actually be the behavior of the cell plus some more constraints will get added. To make a battery pack, a very simple thing is done. Cells are put in series or can be put into parallel, and there are several different methods of doing that. Before I do this, let me talk about what does a battery pack design means. Battery pack design is number of cells are assembled together to form a battery pack for required voltage and current. Voltage and currents are given for each cell. Now, you want this voltage and this current capacity. So, you pack them together. The issues that you need to deal with is first safety issue. Now, cell is cell, it is given, cell in itself is never used, it is a pack which it is used. So, immediately you look at the safety issue. The second very important thing is what is called cell balancing, and I will come to the cell balancing in a short while, because there may be two cells in parallel, but they may not be charged equally. If you are trying to charge two cells in parallel, will equal amount of current go in both of them? Will equal amount of charging will take place? What if 5% more current goes into one and 5% less in another? The cells in parallel are considered to be imbalanced. As we will go on, we will further look at it. Imbalanced cells hurt the cell life and battery life. As you start using battery, the cell, if they are imbalanced, the imbalance will keep on increasing. After some time, the pack will become useless. So, an important task that you need to do in battery pack is cell balancing. We will show you need to do a very careful electrical design, so that every cell is equally getting charged or discharged. Cell balancing can correct for a small difference, cannot correct for large differences. So, pack itself has to design that actually the near same current will go. So, that is, but in spite of that, if there is a, because the internal resistance changes of the cell, maybe there is imbalance, and that correction can be done by cell balancing. So, essentially the battery pack design itself consists of three parts. One is the pack design, you take cell and you do the pack design. And that time, besides these issues, the other thing that you have to worry about is the thermal design. What happens when the pack is being used? Is it getting heated up? And what is the impact of when it is getting heated up? Is the heat getting dissipated? Thermal design will become very critical, because if the pack temperature goes up, remember the cell temperature will go up, cell temperature can be even higher than the pack temperature. And remember that I had talked about at 25 degree centigrade cells behave very well, as you go to 35 it does not behave that well, at 45 it behaves much worse. So, thermal design becomes extremely critical. The second design consideration is what is called mechanical design. When cells are packed together and connected together to even bus bars and put into a vehicle, the vehicle goes through all kinds of rough roads. As the vehicle goes through rough road, the pack vibrates. As the pack vibrates, it is possible that individual cells may vibrate. If individual cells vibrate, the gap between cells will increase decrease. One, it will impact the bus bar connection. Second, you will also find that because of the thermal issues, many of the cells tend to bulge, and if they are bulging and they are vibrating, you can result into very serious problem. So, you have to design the mechanical design of the cell pack has to be done, so that while it allows for some amount of increase, some amount of the what is called the cell getting expanded, some amount, but not beyond a certain point. It does not allow, it compresses, while it tend to bulge out, it will be get compressed, and differential movements are minimized. This is a mechanical design. Then, as I told you, a battery management system will be very crucial. It will take care of safety issue and cell balancing, and finally, the electric design. What about cell in itself? I talked about cells earlier. I am not going to talk too much about cells, but cells depends on the chemistry, and it whether it is a pouch cell or cylindrical cell or prismatic cells. It is a highly controlled process making the cells, and if you remember, watt hour per kg, cost per kilowatt hour, and life cycles are critical parameters. So, what is it? If I take a battery which costs 100 rupees, about 35 rupees will come in the pack design, 25% will come in actual cells, and the remaining close to 35 to 40% is the actual raw materials used. The raw materials used itself plays a very important role. Nickel, lithium, manganese, cobalt, nickel. So, I buy these raw material, I will make cells, then from the cells I make pack, and 40 rupees for raw materials, 25 rupees is a actual making of cell, 35 rupees for battery pack. This is approximate, it varies from pack to pack, varies from cell to cell, but this gives you some idea. Materials depend on the chemistry, quantity of materials used. So, you again look at watt hour per kg. If you want to design a 10 kilowatt hour pack, you calculate how much kg of material you require, and therefore, how much kg of lithium, manganese, cobalt, nickel you require. That is how the cost is also determined. So, thermal design basic objective is to remove the heat generated from the pack immediately. Ideally, temperature should remain constant, as close to 25 degrees centigrade. Mechanical design, so that cells do not budge and the right pressure is applied to the cells, and battery BMS, only balanced cells used in a pack. So, when you select cells, you like to use a balanced cell, and requires, and after that you monitor the voltage, current, temperature for each cell, and then carry out the balancing during charging as well as discharging. Now, one of the most important thing is something can go wrong and cells can get heated. As soon as cell goes above, any cell goes above a certain temperature, you immediately shut down the whole battery. It does not matter, let the vehicle stall, because if you do not, you are carrying out the risk of blowing up the battery. If there is a redundant battery, of course, the alternate battery can take over. So, if you ever use lithium ion cells or cells like this into a vehicle, in a aircraft, you have to worry, because there can be a situation where you suddenly shut down. In a vehicle, if you shut it down, well, the vehicle will stop. You will have to stop the vehicle on the road. You may create a jam, congestion, but still you are safe. Aircraft, you will have a more serious problem. So, pack should get cut off if the temperature increases, key to safety. During charging time, the cells and the pack will continuously communicate with the charger and decide how the charging should be done, how much current should be put, do not put extra current, how much voltage should be used. Remember constant current, constant voltage that I talked about. Battery pack design, let us get to the electrical part of it. Battery pack designed to get a certain voltage and capacity in terms of watt hour or ampere hour. I want this is the capacity and this is the voltage. That is what a motor will require. It requires, let us say motor says I can work at 350 volt, or I will work between 325 and 375 volt. So, your battery pack has to design between 325 to 375, 325 when it is nearly empty, 375 it is nearly full. Remember, one big problem is, since you are talking about, suppose you are talking about a 48 volt battery and you are talking about a 5 kilowatt battery, you are talking about 100 ampere. So, if on the other hand, if it is a 48 volt battery, at times you may require 8 kilowatt peak or 9 kilowatt peak, you are almost going to push 200 amperes. Now, when you are pushing currents of this kind, there are multiple issues. First of all, resistance of every cable will make a difference. Earlier we assumed cables are zero loss, zero resistance, not so anymore. Between cell to cell, the connection will make a difference. What kind of plating are you using? The resistance, smallest resistance, milliohm resistance multiplied by 200 amperes is how many? If I take, let us say, a 5 milliohm or 3 milliohm resistance and multiplied by 200 volt, what have I? 600 milliwatt, ampere. So, sorry, milliohm into, no, I have to do, not I square R, 200 ampere. Suppose I do 200 ampere, then the voltage is going to be 0.6 volt. Now, that can be the difference. Now, 0.6 volt, I have a 4.2 to 3 volt, 4.1 to 3 volt cell. My 0.6 is a drop in the connector itself, connection itself, in a cable itself. The voltage that I will get will be very, very different in that case. I can get into serious trouble. So, and if I have two cable, one giving you, let us say 1 milliohm, another is giving you 4 milliohm, there is a 3 milliohm difference, there will be a 0.6 volt difference between two cells. One is nearly full, one is nearly empty. It is a horrible thing that it can happen. So, remember you are dealing with very high current. So, you have to very, very accurately carrying out the electrical design. Of course, it will also give you I square R losses, I square into R, that is a very, very high losses also. So, depending on the kilowatt hour of storage, certain voltage is preferred. For example, you do not want very high current. So, if you want 5 kilowatt, 48 volt is just about okay. If you want 10 kilowatt, that is worry. 20 kilowatt, 48 volt cannot be used, maybe 350 volt is used. 48 or 72 volt is okay for 2-wheeler, 3-wheeler. 100 watt hour to 15 kilowatt. 15 kilowatt hour itself is 300 amperes, already very high, not good. So, this is something that you have to worry about. 1 kilowatt hour requires 21 AH cells, 21 AH. Now, 21 AH is not possible in those pencil cells, cylindrical cells, of course, unless you put a number of them in series. So, it is possible only with prismatic and cylindrical cell, because 1 kilowatt otherwise will require 21 Ah and you cannot put too many of them in series and parallel, you will end up into trouble. So, 115 kilowatt hour can become a problem. 350 volt is commonly used for a medium size batteries for large cars and pickups. Now, here you can do a 20 kilowatt, 20 kilowatt divided by 350 volt, you are less than 100 ampere. 70 kilowatt hour will be 200 ampere, but there is something wrong in this 1 kilowatt battery pack requires 3 ampere, less than 3 ampere hour. Well, yeah. So, if you do a 1 kilowatt hour battery pack at 350 volt, you require less than 3 ampere hour. Now, that is not possible except for cylindrical cells. So, you can only make large packs, you cannot make small packs with 350 volt. Half a kilowatt hour is theoretically also not possible. You will require a 1.5 Ah. 750 volt is another voltage. Here 60 kilowatt hour to 300 kilowatt hour is used. If you use cylindrical, too many cells will be used. We will get into this, but this is how the 3 voltages come and are used. Let us look at how do you build packs from cells. Typical cell capacity voltage is typical voltage is 3.7 volt from 3.1 to 4.1. Cell capacity is 3.4 Ah for cylindrical, 50 Ah, maybe even 60 Ah for prismatic cells. So, you have to require a number of cells in series. For example, it is a 3.7 volts, and if you want 48 volt, you need 14 cells in series. It will give you 51.8. If you want to go to 350 volt, the number of cells in series will become almost 6 times, about 7 times, about 100 cells. Because it is the 3.7 volt into 100 cell will give you 370 volt. But even if you get this in terms of voltage, what are the current? A single cell, depending on the cell that you use, can only give you so much current. If you want more, you have to put more number of cells in parallel. So, if you for example, take 50 Ah cells, prismatic cells, and you take 8 of them in parallel, that will give you 400 ampere hour. If you use cylindrical and you have only 3.4 Ah, and if you have to get 400 ampere hour, how many you have to put in parallel? 125 cells. You can just imagine what will happen. Generally, cells has to be connected in series and parallel, and there are 2 mechanisms, what is called MPNS, M parallel and N serial. But what is also important, the order is also important. One is MPNS, another is NSMP. MPNS basically means you will take M cells first in parallel, that will form a module, M cells in parallel, and then you put N such modules in series. Not so with NSMP. NS, first you put the cells in series, N cells, then you put in parallel, and we will look at both these designs, MPNS and NSMP. You will see NSMP is not a good way to design and it is not used. It is MPNS that you will design, and MNN can vary. So, 4P14S, what does it mean? There are 4 parallel cells and 14 in series. 14 in series you can calculate, 14 in series will give you 14.3 into 3.7 or 51.8 volts, not ampere hour, 51.8 volts. This is a volt. 4 in parallel, now depends, suppose I use cylindrical cell of 3.8, I get 13.6 Ah. Okay, this is a 13.6 Ah. So, total capacity in kilowatt hour is now this 13.6 multiplied by 151.8 volt. So, the ampere hour multiplied by 4 volt will give me watt hour. So, this is a 705 watt hour with 4P 14S. What if I did 14S first and then 4P? Well, I will get the same capacity. Capacity does not change, but you will see the other impact of it. So, in a very simple way, you can say 4 into 14, 56 multiplied by the capacity of a cylindrical cell, capacity of the cell A in AH multiplied by 3.7 volt, that is the total capacity. But now let us go back to MPNS and NSMP.